Okay, welcome to class meeting 16 of EECE574, the graduate level probability and random processes. No much announcements, except there will be a homework that is giving you the opportunity to take the midterm again. Actually, you are not taking midterm, you're going to solve the midterm problems again. Our TA will post the homework in the PLMS, just saying that the due is 1 week away, for example, solve every problems in the midterm exam. And in this time, it should be noted that collaboration is encouraged. So what is important is that you know the contents in the first exam. Got it? Hyunjung, please let Jiyook know that. Okay, collaboration is encouraged. Okay, no corrections. And here goes the overview. We are still here. Last time I spoke a lot about the meaning of ergodicity. And I believe you much better understands the notion of ergodicity than before. And today we will see more quantitative. Yet last time it was more qualitative. I was talking about too much about the meaning, implications. But today we are going back to math, okay? And then I hope we can move to the next topics. So last time we stopped here. We stopped here. Yeah, and we'd better review a little bit more. So here, first, we start from definition. We define a random process that is mean ergodic, okay? Or ergodic in the mean. You will see today very, very confusing statements. Sometimes this mean appears before the word ergodic as this mean ergodic. Sometimes it will appear after the word ergodic. They mean the same, got it? So mean ergodic and ergodic in the mean means that you take the time average of the random process. In general, this time average is what? Is a random variable, right? Because it's a random process, and the operator converts a time function to a scalar. And you have a scalar with uncertainty. So in general, it must be a random variable. However, that is equal to a constant. That is the, time function. That is the ensemble average of a random process. How can it be possible? A random variable equals a deterministic time function. There is only one way. The random variable is constant, right? And time function is also constant. Got it? So there are some necessary conditions, right? However, anyway, the definition says that a random process is called mean ergodic if your time mean, time average equals statistical mean, ensemble average. So two means, two averages are the same. Got it? So notion is simple. However, there are subtleties, as you will see soon. Okay. Last time I had a typo, but anyway, so let's think about the this time average part first. And this is what, by definition, is the limit of this strange random variable parameterized by capital T. So you have uncountably infinite number of random variables that converges to this ensemble average, which shouldn't be a function of T, right? So it's talking about some kind of convergence over random variables to a constant, right? And as I told you, there are 4 modes of convergence over a sequence of random variables. And we've learned only one of them, that is called mean square convergence. What was that? So let me review what was the mean square convergence. First, you must be given a sequence of random variables. So given a sequence of random variables, let's say xn. So you have x1, x2, x3, dot, 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 and you have another target, the limit random variable, and a limit random variable x. Got it? So this is the setting. Xn converges to x in the mean square sense if. By the way, when you have a block of definition, if means if and only if. Got it? It's not a theorem. In theorem, if and only if, they are different, right? However, in the definition, if is if and only if. If what? If you take the difference, and that difference must be very, very small for sufficiently large n. But that is very small to show that you take the mean squared error. And that is very small for sufficiently large n is translated to this mathematical expression, as you already know. By the way, this expectation for each n is what? Is a real number, right? Because you computed the expectation of some random variable. So that is scalar, but indexed by n, right? So it's like you are given a sequence of random variables and a target random variable. Now, in order to say that, say this sequence converges to the target limit random variable in the mean square sense, you have two things. One is the sequence of real numbers now, and you have the limit of the sequence of real numbers. Got it? And this is the definition. And there is a notation and denoted by what? This part is also very important because mean square convergence is so important and repeatedly used. So they want to say that, okay, xn converges to xn, x, but well, this may confuse us. So let me put dots, okay? And they say what? Okay, let's read it. Xn converges to x in the mean square sense, or limit in the mean of xn equals x. Got it? So that was the definition we've already saw. Now, since we only have a single definition studied yet, let's use that to derive some results from this definition, okay? So what we are going to do from right now is that given the definition of mean ergodicity of a random process, let's try to find out some necessary condition or sufficient condition, or if possible, necessary and sufficient condition for a random process to be mean ergodic in the mean square sense. So it's like, see that? We want to prove something, mean ergodic in the mean square sense. This sounds okay, but this in the mean square sense does not work well with this statement, right? Ergodic in the mean square sense. So people say that mean ergodic in the mean square sense rather than ergodic in the mean square sense, because it confuses you a lot. Got it? But anyway, here mean ergodic is what? What does that mean? We are dealing with, we are testing the time average equals statistical average. We are testing that. In what sense? In the mean square sense. Got it? Mean ergodic in the mean square sense means that. mean. Okay. So here goes the assumptions for some useful result. And these assumptions are very technical assumptions. We don't need that. Okay. What we need is only some of the constraints, and which makes sense. First, x of t has a finite constant mean. Of course, right? Because left-hand side is random variable. it's not related to any time parameter. Right-hand side is in general time function. They can't be the same. So the first thing is that the right side, right? This one must be a constant. Obvious, right? And you remember that in order to talk about the ergodicity, we have to remember this Venn diagram. So you are given the set of all random processes. And here is a very, very small subset of random processes called stationary random processes, or stationary to order 1 if you want. And in this case, probably we are talking about stationary to order 1, or just the subset of random processes that has constant mean. Got it? And in this, given that the definition of wide sense ergodicity may have intersection and may have this area. However, if we restrict our definition of ergodicity as time average can replace statistical average, in that case, ergodicity is a very restrictive subset of stationarity. I'm repeatedly tell you, this is true in a narrow sense. Got it? In a wide sense, they have something like this, right? But anyway, so our stating mean ergodicity, we need mean is constant, obviously, in this sense. So that is the first line. Got it? And the second line is somehow we may not understand why this statement is there. But anyway, it says random process is bounded. It seems understandable. However, this statement, very simple statement, is again very complicated. What does that mean by random process is bounded? We know the meaning of a continuous time signal is bounded. You can choose a finite number, for example, capital M, and you choose 2 upper and lower bounds, plus M and negative, positive M and negative M if M is positive, right? And then the function value is always less than or equal to capital M and greater than or equal to negative capital M, right? That is the definition of a function is bounded. You must be able to find some finite number M. Now, what is the meaning that a random process is bounded? What does that mean? This is also related to what we are going to study in chapter 7. For example, this may be x of t is bounded by, so there exists some m positive such that this is true for all s and t. And you may say that, hey, what is s? You know that actually this is what? This must be written in this form in a major theoretic sense, right? For every sample s, you have a time function. So for all s and for all t, this must be true. That is what? Everywhere bounded. However, in the probabilistic statement, this is unnecessary. So this is, by the way, surely or everywhere boundedness. And more useful thing is almost sure boundedness. What would be that? There exists M positive such that probability of event that equals 1. See that? Here, this is the probability of some event that is 1, right? What event? You have some S, right? And there are some samples that violates this condition. Your sample path cannot be bounded sometimes. And for some S, your sample path is bounded. Now you have 2 subsets of sample paths of x of t. And now you compute the probability of this event occurs, bounded. And you compute probability of that event, not bounded. You compute. Then this probability is 1 and that probability is 0. In that case, we are happy. Got it? For example, you can do this. We generate a number from 0 to 2 pi uniformly, right? And then for every number except 0, you assign a bounded signal. And now you assign, for example, what kind of signal do we have unbounded? Yeah, e to the t, exponential function, e to the t. That is what? That is unbounded, right? For what? For the uniform sample 0. Now you know that probability of your angle, the theta random variable equals 0 is 0. So in this case, this is true. Almost surely your random process is bounded. That is different from this, right? Because theoretically speaking, your some interval, including theta equals 0, is non-negative, right? So that means there are some sample passes that violates this one in this example. So almost sure boundedness may be very useful. Another one is that bounded in some other sense, blah, blah, blah. So actually, even though I copied this statement from the textbook, since I didn't look up the original theorem that proved very rigorously what we are going to see, I didn't see that. I myself does not know whether the author of the book meant this one or that one or something else, which means that you don't need to know exactly. But anyway, there is a statement, x of t is bounded. Yeah. And this is not, yeah. This looks like that one, but probably the author meant this one. I do not know. I didn't look up the original proof. That would be proved in what? Probably in the 1950s or 30s. I don't know, right? In some mathematical journal. I didn't see. So anyway, so bounded random process. And then the third one is a little bit strange. What does that mean? So here you have a time function, right? You have a time function. And what? This is in general a time function. And you compute that one, and it seems something's wrong, right? We already have a constant mean, right? And if it is constant, finite and constant, then this should be true. So I myself cannot understand why the author put this one here, because it seems that the first one and third one means the same, okay? Anyway, and here goes a statement that is quite interesting. This textbook, the author of this textbook says x of t is regular if this holds, but I myself was taught in this way, second order process. But this is very dangerous terminology. I would rather love this. But anyway, what does that mean? By a random process is, how to say that? The expectation of instantaneous power is finite. What does that mean? Yeah, you think in the other way. That is not infinite at any t. So as you see here, it seems that the first statement shouldn't be here. Then we can talk more about that one and that one. Yeah, because if it is, yeah. Anyway, so regular process is defined in this way. Let me define a continuous time random process is regular. Here, I didn't assume stationarity because definition of regularity is much bigger. Okay, if random process x of t is regular, if expectation of x of t modulus squared is finite for all t. Okay, but in our case, we may, yeah, or sometimes it is called a second order process. X of t is a second order process. Second order process. If the ensemble average of instantaneous power is bounded for all t. I do not love this copy from the textbook. Anyway, so under certain conditions, that is what we say, okay, as an engineer. Under certain conditions, we are going to prove the necessary and sufficient condition. So let's see. First, we remember that this is a random variable in general, right? So let's start defining a sub x as the random variable, the limit of this time average. Got it? Finite time average. So you started from a of x. And now, since we are talking about mean square convergence, what we can do is to calculate the mean and the variance of this random variable. So we start from calculating the mean of the random variable. So you define that one. This is a random variable. And you compute the mean. Simple, right? And let's see. So this is the notation, and here goes the computation. So you just plug in that definition here, and our assumption actually allows us to change the order of this limit and that limit. Okay, I don't know exactly why those technical conditions are required, but usually those technical assumptions allows us to change the order of two limits. Got it? Anyway, so this expectation goes in up until here. And we know that, and we assumed that the mean path is constant. So here is a constant. And we already know that a constant is what? Has what? Constant time average. So we have a constant. So mean is constant, obviously. So this has the same mean as the random process. Got it? So you must remember that this is expectation of x of t. And this is constant. Now, we are going to use the variance. And here goes a strange trick. We do not start from variance of ax. We use it here. Got it? This is the variance of ax. And we suddenly start from Chebyshev inequality, and I hope you know that. Okay? As I told you, just before we start today's meeting, I spoke in Korean and talked about the importance of undergraduate level probability, those stuff. And I remember I taught when I was teaching the undergraduate probability random processes, I taught this Chebyshev inequality. Anyway, since many of you forgot what is Chebyshev inequality or never heard of, let me restate that one. Got it? First, we need the Markov inequality. What is the Markov inequality, by the way? Markov inequality. Given a non-negative random variable, that starts from this. Okay. Definition. A random variable is non-negative. What does that mean? Non-negative. If probability of event that x is non-negative equals 1. Got it? So whenever we state something, we state in terms of probability. That is the first thing in the probability theory. Got it? A random variable non-negative if the event that the random variable non-negative has the probability 1. Okay. Now here goes a theorem or lemma because it's too simple. But anyway, given a non-negative random variable, now what we are talking about is the tail probability, especially right tail probability. Because if you just consider, okay, by the way, let me visualize that. So suppose this is the we don't need a 2-dimension, but anyway. So you have a random number generator, and saying that generates a non-negative, that is a non-negative random variable generator. Now you push the button so that you have a lot of outcomes, and you draw a 1-dimensional scatter plot. What happens? No dot occurs here, right? Because you always have non-negative numbers. But nothing here. Okay, that is not true, but you can assume that, okay? The probability that you observe something here is 0. So actually, you may have you may have that. But anyway, so given a non-negative random variable, so from the scatter plot 1D scatter plot, you can kind of guess the empirical PDF probability distribution. For example, it looks like a Rayleigh random variable, for example. And then what you want to do is to talk about the tail probability. So here goes a trick. Some people use equality, some people do not. But what do I do? Let me just do not use it. Okay. Yeah, it's subtle, but anyway. So the probability event that x is greater than some constant x. Okay, you choose it. And what can you say that? Okay. Can you say something? It's too general. You didn't specify anything except x is a non-negative random variable. It's very, very general statement. But to say something, you need more assumption. Okay, so here goes another assumption with some and you may say that, hey, that's obvious. I have a random variable. I have a mean. Actually, that is not true because some random variables does not have the ensemble average well defined. If you want to compute that one, because it's kind of limit of something that could blow up, it may have infinite mean. Okay, so here means that is finite. Okay, so you have finite mean. Okay, so suppose you have a non-negative random variable with a finite mean, then you can say something about tail probability without even knowing anything about the distribution, except that there exists a finite mean for this non-negative random variable. What was that? Anybody? This tail probability, this probability. Anybody wants to say about this probability? Yes, definitely that is less than 1 because it's a probability, right? So you can say, okay, I have no idea that this must be less than 1, but that is not what you want to say. We want to say something more than this. And that more would be less than something in general, not 1, right? So what? Anybody? Less than or equal to or less than something. So here goes the mental model you have to remember related with Markov inequality. Whenever someone say Markov inequality and you do not remember anything, then you remember this figure. That figure is very interesting thing. Okay? That figure is something like this. Let me use A rather than X because this is confusing. Let me just use A, okay? This is X-axis and this is A. Got it? And here, what you want to draw is some unit step first, right? And as you know, in probability theory, we usually use right continuous unit step. So here, the value is 1, and here, the value is 0. Got it? And then what you do is this. Since you just talk about the linear thing for the expectation, you draw a straight line that crosses the origin. What is that? That is y equals x over a, right? Am I right? See that at a, the value is 1. At a, the value is 1. So they meet here, right? Then you first find one inequality. What is that? What inequality do you have? But on this reason, what you can say? X over a is always greater than or equal to u of x minus a for all x greater than or equal to 0. Am I right? See that? On this non-negative interval, these two graphs of functions meet here and here only, right? So I have equality here because they are the same at x equals 0 and x equals a. Got it? Now, just a second. Then probably I need, I need equality here. Just a second. Yeah. Okay, let me proceed. Okay. Now, what you can do is that from here, you have this inequality. Am I right? See that? X is non-negative random variable. And this is true. Can you get it? In order to have this one, you may have confusion, but let's go back to this scatter plot. So you generate a lot of dots and now test whether this is true or not, which means that here you have a lot of dots, right? Millions, trillions. What happens? Whatever x you have, your x divided by a, that follows this value, is greater than or equal to u of x minus a, which is either 0 or 1. Am I right? From this figure. Then this probability is 1, right? Because you only have this probability equal to 1. Got it? So from this assumption of non-negativity of random variable x, you have another probability that is equal to 1. So that's why I'm asking you to remember this figure, to remember what was the core or essence of the Markov inequality. Then the next step is kind of very obvious. What is this, by the way? Just a second. Yeah, and another one is this one. Yeah. First, we talk about probability, and next we talk about the mean, because we assumed something related to the mean. Got it? So from this one, the first thing is this one, and second thing is what? We take the expectation on the both sides. So you have that one, and you take the expectation. Now, what is this expectation? By definition, that is mu x divided by a, right? So left side is mu x divided by a. And what is the right side? I will flip the left side. What is this one? Probability that x is greater than or equal to a, right? Because expectation of something is what? This may confuse you a lot in the beginning. Expectation of something is value times probability. So u of x minus a is 1 with the probability that x is greater than or equal to a, and it's 0 if x is less than a. Got it? So you have this right-hand side now going to left-hand side is probability of event that x is greater than or equal to a. So it seems that I have to have here equality, and here equality, and here mu sub x divided by a. Got it? So you have an amazing result like this. As far as x is a non-negative random variable and it has a finite mean, then you can say something. It's like, hey, I have no other information. Say something about tail probability. And you say that, okay, set A. The probability event that you have observation greater than or equal to A can be bounded by this number. And actually, here is a trick. Suppose mu sub x is very, very large for this one. And your A is just some value, 1 over 2. Then what happens? This upper bound may be million. That's same as probability of this event is 1. So in many cases, with very large number, mu x divided by a, the Markov inequality does not mean much. Got it? So it's like this. Let's plot that one. And by the way, what is this one? This is very similar to the complementary CDF, right? Be careful. Since we have equality here, it is not exactly the complementary CDF, because CDF has equality, right? CDF of x, capital X of x, CDF capital F sub capital. Be careful. What was the definition? Right? So if we put here, it's not CCDF, complementary CDF. That's why I wanted to skip that one. But anyway, let's just assume that this is something similar to the complementary CDF, right? Then usually it goes down, right? It's non-negative random variable. So here you have 1, right? The CCDF of non-negative random variable is 1 here. And it may go down monotonically, right? And what is that one? If you choose some A here, right? Then you plot mu x divided by A. That is what function? Some function like that, right? And that would be wrong. Let me draw differently. Something like that, okay? And what you say is this, okay, I have a function, mu x over a, and this function upper bounds this function that is almost the same as a CCDF. Your complementary CDF can be bounded, especially when x is a continuous random variable. You can say that because this is exactly, even with equality, you have complementary CDF. Got it? So in general, not in general. In general, for continuous random variable that is non-negative, your CCDF is always bounded by some curve that is inversely proportional to your CCDF value as your level or cut point. Got it? And that is kind of interesting, right? And this coefficient is just the mean. You assumed finite. Got it? So if this is infinite, you can't say anything. So this is the Markov inequality. Now, what is Chebyshev inequality? That is the question. And I need more space. Just a second. And here goes the Chebyshev inequality. Sometimes it starts from T. I don't know exactly. Sometimes Chebyshev. So probably here in our textbook, Chebyshev. Okay, Chebyshev. It's really confusing. I exactly do not know what is this mathematician's name. Okay, but anyway, Chebyshev inequality. So if you were an old-time mathematician, some person named Markov have found a very interesting upper bound, saying that, hey, given any non-negative random variable with finite mean, I can give you an upper bound curve that upper bounds your complementary CDF. Oh. Now, you are very envious and you want to do something more. What would be the next thing? And so you read this theorem very carefully and find, okay, here goes a very general statement, except finite mean. So you may say that, okay, what about infinite mean or mean does not exist? No, that wouldn't work. Then probably you would say that, okay, then probably I will have something similar now with one more assumption that is, for example, finite variance. So it's about first order constraint, right? You may want to have a second order constraint and saying that, I have a good idea. So very envious Chebyshev. I didn't say he was very envious, but I in the imaginary world, here goes a very envious Chebyshev starts with a new inequality. What can I say? So probably you may start from this one. Okay, suppose you want to prove something with that one. And here you may say that, well, why you need x squared? Because I started from here. So let me delete this one and let me start again. Okay. So this is the start point, right? Am I right? This is the start point. And I define x equals some y squared. Here, x is a non-negative random variable. So it's greater than 0 with probability 1. By the way, this means probability of event equals 1. Got it? This is very popular shorthand notation. WP1 with probability 1. Probability 1. Got it? So non-negative random variable. And let's replace x with some random variable squared. And this is very amazing idea because here y can be, y is not necessarily, we don't need that one. Because given any real random variable, y, its square is always non-negative with probability 1, right? Hey, I removed that assumption of Markov by squaring it. Now let's see what happens. So I replace like this. And here, well, I must have, because this is expectation of x, and x is now y squared. You have that, right? And what do you need now? You need assumption on that one, finite. But if you remember, this requirement also requires x is finite, and second order, sorry, y is finite. Y squared is also finite. Okay, so as a master's degree mathematics students, Chebyshev first come up with this idea. Hey, I successfully extended Markov idea, and you go and Chebyshev goes to his advisor and saying that I have extended, and your advisor says that too simple, make it more complicated. So what do you do? Any idea? Any idea? Anybody? Yeah, so you subtract mean and then approach. So what you do is this. So okay, your advisor was not happy. So what you do is this one. And you somehow change to epsilon squared, for example. And now let's see this. What can you say? You replace x with y minus mu y, because we assumed mu y is finite. And then what? Epsilon squared, because a is replaced by epsilon squared. And you have suddenly variance of y. Right? Hey, good idea. Okay? So now you have something interesting. This part can be replaced by what? You know this trick, right? This was the Chebyshev's idea. It looks like does not involve any squaring here. But actually, you know from your middle school mathematics, actually, this event is the same event as that event involving squaring, right? You know that they are if and only if statements, right? For any real number y and epsilon, mu y, right? And this upper bound involves only the mean and the variance, the first order and second order property of any random variable. Y shouldn't be restricted to a non-negative random variable, because anyway, you made it up to the Markov inequality. So you made a link between the mean and variance and this inequality with Markov inequality. And let's see the same thing like that one and that one again. Because I personally have found that not many textbook, probability random variable processes textbook plots this and that at the same time. Some textbook, many textbook, as you've seen, draws that one, but not this. Okay, and very few draws that one without drawing that one. Now let's draw two figures for the Chebyshev inequality. Anyone wants to do that? Anybody? So I'll give you 5 seconds for you to invent your own plots. So we start like this. And let's see, what does this mean? This is y-axis. And now suppose you generate a lot of outcomes from your random number generator marked by y. What happens? You have here some finite mean mu sub y and a lot of dots, right? And what is this event? This event is the event that from the mean, right? You always interpret something like this as what? From this, from A to X and distance, right? Means that from mean value of random variable, your realization has distance greater than or equal to epsilon. So what you do is that here is mu sub y plus epsilon, and here mu sub y minus epsilon, and you have what event? That event, okay? Outside this interval with length 2 epsilon, got it? Now, as you know that, as you guess, what we assume is that if mean and variance is finite, most of the dots are gathered together, close together, this mean somehow, right? That's obvious, right? That's the meaning of mean value. It would represent the center of mass of these dots, right? So the probability of this tail, now you have two tails, tail probability is very small or bounded by some number. It is definitely less than 1. So what you do is this one. You start from that one, and now you draw a second degree polynomial. That is a parabola. Sorry, it shouldn't be. Okay. So let's say this is origin. Okay. And here's mu sub y. And what do you want to do? What you want to do is that you have something like that. Figure is wrong. Let me draw again. This is one. You have that one. You have that one. Yeah. And here goes a second order function. This is u of y minus, be careful, mu y plus epsilon. This is y, mu y minus epsilon minus y. Okay. Yeah. Say that this unit step function has value 1 if the argument is non-negative. Means that y greater than or equal to mu y plus epsilon is 1, right? Now see that this unit step function, it looks strange, but our simple approach is that argument is non-negative, which means that y is less than or equal to mu y minus epsilon, then it is 1, right? So here, unfortunately, we have a right continuous function, but anyway. And what you can say is these two curves, right, is upper bounded by this parabola. And what is this parabola? It has center mu of y, right? And if it is evaluated at mu sub y plus epsilon, then it must be 1. So you have what? Something like this. Am I right? So you plug in mu sub y plus epsilon, then mu sub y cancels and it becomes 1, right? So what you can say is that this parabola is greater than or equal to that one, and you can say that sorry about that. Sorry. Am I correct? Just that. I hope I'm correct. Yeah, something like that. Okay. So this is greater than or equal to 0 means either that one is true or that one is true, right? Got it? So what is the difference between Markov inequality and this Chebyshev inequality? You use a parabola, second degree polynomial, rather than first degree polynomial, which is a straight line. And you use that one to bound some unit step function. Why do we do that? Because unit step function, which is evaluated by expectation, gives us some probability of something. As I once told you, probability is a special case of expectation, right? See that? Probability of some event, A, equals what? Expectation of indicator function of A. So what? This is either 1 or 0. So value 1 times what? Probability of A plus 0 times probability of A complement. So if you remember this function, indicator function, is very useful to link probability and expectation. That's why we use first straight line to bound a unit step function. And in the Chebyshev inequality, use parabola to bound a kind of unit step function. Got it? And that's the difference between the Markov inequality and Chebyshev inequality. And then what do we have? So we do the same thing. If you take the entire probability, that is 1, right? That's too obvious. So what you do is just be careful. Take the expectation on the left and right side after we replacing it y to random variable. You can say this. Scale. Got it? Be careful. Here, this is for a variable y, right? For all y. And this is what? For all random variable y. Got it? Now you take the expectation on the both sides. Then what? What is this one? This is the variance of y divided by epsilon squared. And what is this one? Probability of an event that you have some tail observation, right? Deviation from the center is greater than epsilon. Or what you want to do is that y minus mu y less than or equal, greater than or equal to epsilon. Got it? Now, the last part, we draw what you want to plot, the kind of CCDF. So the next step is to find something like this, right? Unfortunately, we don't have CCDF because we have two sides, right? But anyway, what we can do is like this. Let me not do this, just a second. So it's kind of complementary CDF of what? Absolute value of y minus mu y. Got it? Kind of CCDF. Now, what you can say is this one. Here you must have 1 because if you take epsilon 0, what happens? This is 1. The probability that absolute value of y minus mu y greater than or equal to 0 is 1. So you start from here. And you know that if we increase epsilon, it's monotone decreasing function. So it's something like that one. And this is what? The Chebyshev inequality states that your function is upper bounded by parabola as a function of parameter squared. Got it? Now, which one converges faster? Markov inequality and Chebyshev inequality. You know that 1 over x converges to 0 much slower than 1 over x squared as you learned in middle school math and high school math. So we can say that Chebyshev inequality is better than Markov inequality. And you may wonder, what? Something strange. So let's do this, okay? Suppose we just use Markov inequality here. What can we say? Markov inequality. What can we say? Just view this as a non-negative random variable and try to find this probability. Then your Markov inequality say that this is upper bounded by what? Expectation of y minus mu y, right? Divided by epsilon. And probably this mean is finite, right? And then you have 1 over epsilon. So what I guess is that you have something like that. And that converges very, very slowly than that one, okay? So anyway, as far as variance exists, right? And also computation of this expectation of absolute deviation is difficult in general. Anybody knows what is this value for the Gaussian random variable? You remember? Nobody remembers, right? Right? So Chebyshev inequality is much better because it relies on the mean and variance of any, not necessarily non-negative random variable. And probably up to this point, you've heard about these two inequalities somewhere. But probably you've said that, okay, so what? Yeah, I also myself, when I was teaching an undergraduate course, I just stopped here. Even I didn't draw that one because my textbook didn't draw. But here goes a very useful use case of Chebyshev inequality. Now we are back. Let's see. So as you see, the assumptions we made were all related to the first order and second order expectation, right? Second order moments. And that was the reason, actually, to use the Chebyshev inequality that relies on the second order moments. So what we do is that after we define this random variable, parameterized capital T, we first find the mean, and we haven't yet defined that one, but suppose we have calculated that one, then we have this Chebyshev inequality. And you may say that, wait a minute, that is not Chebyshev inequality. You are right in one sense because our original Chebyshev inequality would have said this. Okay, so random variable minus its mean, right? And greater than or equal to epsilon, right? Because it's originally talked about the tail probability is upper bounded by sigma of ax squared divided by epsilon squared. Now, what do we do? What we do is that we convert that one to this one. 1 minus probability of this event. Sorry. 1 minus. Right? They are the same statements, right? We subtracted both sides from 1 and flip the inequality. Got it? Yeah. And then we convert the left side to this one. But here, if we had inequalities here, we must drop this equality, right? Actually, it's okay. So let me delete that one because it's not that important here, okay? We can rederive Chebyshev inequality that does not involve equality. However, it's okay for this case, got it? So this probability is same as that probability because these two are complementary events, right? Completely flipped, greater than or equal to is the complement of less than, right? So these left sides are the same and the right sides are the same, right? So if we drop that one, it's okay. Now, we know that this holds for any epsilon positive. So far, so good. But we want to say what? We want to say something like this. This sequence of random variable, if we choose T, capital T as 1, 2, 3, 4, 5, right? Then converges to this one. We may want to say it. Then what do we need? What do we need? Suppose this variance is 0. What can happen? Probability of something is always greater than or equal to 1, right? By this Chebyshev inequality. What does give us the probability is 1? That is the idea. The reason why we use Chebyshev inequality is that we first have this inequality, which apparently does not mean much. It's a simple application of Chebyshev inequality to this situation. But what you want to say is that if the variance is 0 or close to 0 or converges to 0, we do not know yet, but suppose this is 0, what happens? We can say this probability is 1. That is a very strong statement. And we are going to have that one. So it's like this. Unfortunately, the variance is not 0, but suppose as t tends to infinity, this variance parameterized by capital T goes to 0. Suppose that. Then what happens? Let's see that. Got it? So what you do is that this is all parameterized by T. So let me restate this one. Be careful. Yeah. E. Yeah. And by the way, this is constant, right? So here we have just a constant. And we have epsilon greater than or equal to 1 minus sigma AXT squared divided by epsilon squared. And here we want to let t tends to infinity. And suppose this variance tends to 0 as capital T tends to infinity. Then what can we say? What can we say? This probability of event equals 1, right? So this probability converges to 1 as t tends to infinity. Am I right? And also, suppose if this is just goes to 0, then what happens? For any epsilon, that is true, right? So what we do is that we first show, just a second, something's not correct. Yeah, we shouldn't do that. Okay, just a second. Yeah, okay. What you do is this. So first thing is that we show sigma A x t squared tends to 0 as t tends to infinity. Okay. And then we would have something like this. Am I right? Because see that this is simply a number, a function of t. If you compute this probability, it's just parameterized by capital T and epsilon, nothing else, right? So you fix epsilon first, and this becomes a function of capital T. And then you show that this goes to 0, right? Which means that this converges to 1. Am I right? So first, this is true if we can show the variance tends to 0. And then what we do is that since this holds for all epsilon, right? For all epsilon positive, what does that mean? We take the sequence of epsilon that converges to 0, not exactly 0. Then due to the countable additivity of probability measure, since this is shrinking event, the limit event has the same probability. That probability of limit, the limit of probability of event is same as probability of limit event. So since this holds for all epsilon, we choose some sequence of epsilon that converges to 0, then we eventually interchange the order of these two. And by the way, the countable additivity of a probability measure, it sounds horrible, but it's very simple. It just says continuity of probability measure. And as you remember in high school math, what is the continuity in the simplest statement? You can change the order of limit of function. F of x is continuous at x0. What does that mean? Limit x tends to x0 of f of x equals f of limit of x, x tends to x0. And obviously, what is this one? x0. In your high school math, you said that a function is continuous at x0 if and only if limit of fx when x tends to x0 is equal to f of x0. However, that statement can be restated as this one. Why this trick is important? Because you change the order of these two. So actually, continuity means that you change the order of function and limit. Okay, the limiting operation and functional operation. You can change the order. Same thing happens in probability measure. If the sequence of events is shrinking or expanding. Okay, that's kind of horrible to you, but anyway, so this goes inside, and then what? We eventually have probability of this equals 0 is 1. Something like this. Okay. So eventually what we have is something is true in probability 1. Even though we start from the second order thing, we have that. Okay. So let's see. Let me a little bit more talk more about that. Okay. So what you do is that we compute the variance of AX, the random variable, this one. And to compute that one, you subtract the mean. Here is the mean. And then you should be careful in converting this integral to that one. Okay, you've done in undergraduate math, actually. You have some square area, you convert it to, in the 2 dimension, you convert it to a 1 dimension, and you have this one. So this variance can be computed from your autocovariance function of the random process. And that random process is multiplied by this triangular windowing function. So your integration is simply what? C of xx tau, that should be symmetric in real random process case, and you suppress the tail. So it's like you can replace that one to plus minus infinity, and you can set this value to 0 here, which means that you just observe plus minus capital 2t, which is 4t length observation of the autocovariance function, and you somewhat suppress that one by multiplying triangular function. Now you calculate the integral, and then you let t tends to infinity. So actually, you are given a covariance function, and your triangle is just becoming a straight line. Okay, and if this divided by 2t is finite, okay, or if it converges to 0. If this converges to 0, then your variance converges to 0. Then what can we say? We can say that the process is ergodic in the mean square sense. Okay. Anyway, time's up, and let me repeat the last part next time, because I talked too fast and probably you couldn't understand. Okay, that's all for the day.